Hello and welcome to Precalculus lesson number 41, which will be our last lesson for the Precalculus series. In this video lecture, we're going to learn about Pascal's triangle and the binomial theorem. We first need to understand what a binomial expansion is. When you take an expression of the form quantity x plus y to the n for a whole number n, which is clearly a power of a binomial, recalling that a binomial is just a polynomial with two terms, and multiply it out, the resulting expanded expression is referred to as the binomial expansion of quantity x plus y to the n. For example, given that quantity x plus y squared equals x squared plus 2xy plus y squared, we call x, the result x squared plus 2xy plus y squared the binomial expansion of quantity x plus y squared. What we would like to do now is take a look at several binomial expansions and see if we can see a pattern. So in the first case here we have the 0th power of x plus y, which is of course just 1. The first power of x plus y is x plus y. The second power of x plus y is x squared plus 2xy plus y squared, which we've already seen. The third power would be x cubed plus 3x squared y plus 3xy squared plus y cubed, etc., right? These, of course, can easily be verified through techniques we've learned for multiplying polynomials. Let's remind ourselves of those real quickly. For example, if we want to verify the formula for quantity x plus y cubed, we realize that x plus y cubed can be written as quantity x plus y times quantity x plus y squared. We of course already know what the square of x plus y is. It is x squared plus 2xy plus y squared. So we can just multiply that out. I'll use the rectangle or box method. So we can put x plus y here vertically, and we can put x squared plus 2xy plus y squared here horizontally, and then we'll just multiply it out like a times table. So x times x squared, for example, we know is x cubed. X times 2xy will be plus 2x squared y. X times y squared is going to be positive xy squared, and then for y times x squared we get positive x squared y. Y times 2xy will give us 2x, positive of course 2x y squared, and finally positive y times positive y squared will give us positive y cubed. So we notice that we have some like terms, those two there and these two here. So if we combine those, we end up with, we have an x cubed plus 3x squared y plus 3xy squared, and then plus y cubed, which is of course the expression that we see here and we saw on the previous screen. Now if we wanted to do, for example, quantity x plus y to the 4, we would realize that that can be written as quantity x plus y squared times quantity x plus y squared, and then we would end up with quantity x squared plus 2xy plus y squared times quantity x squared plus 2xy plus y squared, and then we could just multiply it out again using the same technique. So we would just have the same thing both vertically and horizontally, which would be this, right? So we repeat that here. And then again, just make a table here and multiply it out just like we did up here. All right, and then you would find the result that we saw for quantity x plus y to the fourth. Let's go back to our other screen. And if you do that successfully, of course, you'll end up with this. So let's go ahead and take a look at the coefficients only to see if we can see a pattern. What Pascal noticed, and perhaps many people before him, but he's the one who's received the credit for this discovery, is the fact that there is a pattern when you only look at the coefficients, which I've outlined here in red, okay? And the pattern is very interesting because if you ignore the ones on the first and last terms, you notice that, for example, this 3 here can be obtained by adding the 1 and the 2 here, or the 2 here itself can be obtained by adding those 2 ones. The same for this 3, you can add those 2 numbers, 2 and 1, to get the 3. In the next line, for example, this 4 can be obtained from adding 1 and 3, 6 can be obtained from adding 3 and 3, 4 can be obtained from adding 3 and 1, etc. So it's very simple to generate this triangular formation of numbers known as Pascal's triangle. And if we now go to the next page and only look at those numbers, we see Pascal's triangle. So here we have Pascal's triangle for the first 10 rows. The first row is called row 0 because the number associated with the row is basically the power of the binomial that we are raising to a power. So the first row is row 0 because if you remember, that was for quantity x plus y to the power of 0. The second row was quantity x plus y to the 1, etc. So you can see these numbers generated very quickly, like 1 and 5 gives us 6, 5 and 10 gives us 15, 10 and 10 gives us 20, 10 and 5, etc. And you also notice there is a symmetry going on here as well, right? So what you see before that middle term or middle terms, depending on whether you have an even number or an odd number, then it's going to be the same as what you see on the other side. So there's a perfect symmetry here. Now, of course, for example, row 8, notice, has 1, 2, 3, 4, 5, 6, 7, 8, 9. Row 9 has 10 elements. Each row has one more element than the row number. Row 0 has 1, which is 1 more than 0. Row 2 has 2 elements, which is 1 more than 1. Row 3 has three elements. Row 2 has 3 elements, which is 1 more than 2. Row 3 has 4 elements, which is 1 more than 3, etc. And so these are some of the things you want to notice with respect to Pascal's triangle. Pascal's triangle is just a wonder, full of wonders. One of the amazing connections with Pascal's triangle, and this is a quick detour from what we're doing because it's not really related to what we're about to do, but since we've already seen the Fibonacci sequence, I thought you might enjoy this. Notice that if you just do a diagonal cross like this and add the numbers that you see, of course, for the first 2, you're just going to get ones, right? But for this one, you'll end up with 1 plus 1 is 2. For the next one, 2 plus 1 is 3. For the next one, 1 and 3 and 1 gives you 5. For the next one, you get 8, etc. If you look at these numbers here, where those sums, you notice something interesting. This is exactly the Fibonacci sequence that we've seen before, where starting with the third term, you can get each term by adding the 2 previous terms. So 2 is 1 plus 1, 3 is 2 plus 1, 5 is 3 plus 2, 8 is 5 plus 3, etc. So kind of an interesting connection there. Now we'll get back to our main topic. Now we want to look at 4 important observations about the expansion of quantity x plus y to the n. Notice that regardless of what the n is, no matter what power we're raising x plus y to the power of, there are going to be n plus 1 terms in the expansion. The first term is going to be x to the n, and the last term is going to be y to the n. Notice here x cubed, y cubed, x squared, y squared, x to the 4, y to the 4. That is, of course, for n greater than or equal to 1, right? In each term after x to the n, right? So, for example, let's look at this one. Let's focus on this one for simplicity. Notice that the exponent of the power of x decreases. Notice you have here x to the 4, then you have x cubed, then you have x squared, then you have x to the 1, and finally x to the 0, right? So the opposite happens for the exponent of y. The first one has no y, so that's y to the 0. Then you have y to the 1, then you have y squared, then you have y cubed, and y to the 4, etc. The last thing we need to pay attention to is the fact that the sum of the exponents of the powers of x and y in any term is n. So, for example, look at this last line here, which is the expansion of quantity x plus y to the power of 8. Notice that, of course, there's only a power of x here, but if we had the power of y, it would be y to the 0, and then 8 plus 0 would be 8. Here we have 7 for x, and the exponent of y is 1. 7 plus 1 is 8. Notice here 6, 2, 8. 5 and 3, 8. 4 and 4, 8. 3 and 5, 8, etc. all the way to the end, right? Notice that all the things we have said can be reviewed here quickly. It's the expansion of x plus y to the 8, but there is 1, 2, 3, 4, 5, 6, 7, 8, 9 terms, one more term than n here being 8. The first term is x to the n, which is x to the 8. The last term is y to the 8. Notice that in each term, the exponent of x starting with 8 goes down from 8 to 7 to 6 to 5 all the way to 0 in the last term is x to the 0, right? For y, you start with y to the 0, and then you move to y to the 1, 2, 3, 4, 5, all the way to y to the 8. And with those observations in mind, we can now start doing some interesting expansions, which are not just those of these simple binomials. By doing clever substitutions, we can do more complex expansions. All right, in this example, we're going to expand quantity u plus v to the 4 using Pascal's triangle, which I've recreated here, substitution, and the 4 important observations we just learned about with respect to expansions. So basically, we're interested in this row 4 of Pascal's triangle. So the coefficients of interest are 1, 4, 6, 4, and 1. So for the expansion of the 4th power of u plus v, remember the first term is just going to be whatever this first term is to the power of n, which is 4 here, right? And the coefficient is, of course, 1. So 1 times u to the 4 is just u to the 4, so we don't need to write it. Plus, the second term's coefficient is going to be 4. And remember, now the powers of u are going to start going down, so this will be u cubed. And then it's the first introduction of v, because the first term had v to the 0, which is 1, which we don't write, but the next term will be v to the 1, which is just v, okay? And the next term is going to have a coefficient of 6. The power of u is going to go down 1, so it becomes u squared. The power of v is going to go up once. So v squared as well. Notice in each term, the sum of the exponents is 4. 4 here, 3 plus 1, 2 plus 2, etc. Plus the next term, the coefficient is going to be 4. The power of u is going to go down once again, so it becomes u. And then the power of v is going to go up, so v cubed. And for the last term, we know that coefficient is 1, so we don't really need to write it. It's going to be 1 times the second term to the power of n. Notice the coefficient of v went up 1 and the coefficient of u went down 1. U to the 0 is 1. 1 times v to the 4 is just v to the 4. So we don't need to write the u to the 0. But there it is. There's the expansion using Pascal's triangle, the substitution of u for x and v for y. And the 4 important observations that we learned about on the last screen. And there we have it, okay? So very simple, very efficient. Next, we're looking at a cube, but notice all the analysis we've done has been for sums, not for differences. But we'll see what happens when there is a difference. We can always take quantity 2x minus 3y cubed and think of it as quantity 2x plus quantity negative 3y cubed. See, now you can see that basically we're going to replace x with 2x, and we're going to replace what we normally call y with negative 3y. So that's the kind of substitution we're looking at. So the row of interest is row 3 here with coefficients 1, 3, 3, 1. Remember, there's no confusion here. You may say, oh, that's the 4th row. Yeah, but remember, we call the first row 0. So this would actually be row 3. All right, so for the expansion of quantity 2x minus 3y cubed, we're going to have the first coefficient is 1, so 1 times the first term, which is 2x, to the power of n, which in this case is 3, right? I didn't have to write the 1, but I just wrote it for emphasis. All right, plus the second coefficient is 3. Now the coefficient of the power of 2x is going to go down to 2, and we're going to introduce the second term for the first time because we get 3y, negative 3y to the power of 1. Remember, it's better to look at this version, okay? So think of this as the second term, the negative 3y. So we get negative 3y to the power of 1, okay? And then plus the third coefficient is also 3 times, once again, we reduce the coefficient of the first term by 1, so it becomes just 2x to the power of 1. And the coefficient of the second term, negative 3y, remember we're looking at this sum here, is going to go up to 2. And for the last term, it's just going to be the cube of the negative 3y term. And the coefficient is 1. And remember, this one is just going to be quantity 2x to the 0, which is 1. So we don't need to write it because it's times 1. So it's just going to be this expression here. All right, so now we just need to simplify, right? So we get 8x cubed. Now here we have 2 squared is 4 times 3 is 12 times negative 3 is negative 36. Be careful when you do all that. And the x is of course going to be squared and then y. Okay, for the next term we have the square of -3, which is 9 times 3 is 27 times 2 is 54. And because that was being squared, it's just going to become positive. So plus 54 x y squared. And then this last one, the cube of -3 is -27. So minus 27 y cubed. So notice, again, we have 4 terms, even though the n is 3. Remember, we always get one more term than the value of n. Also note that when it's a difference rather than a sum, what's going to end up happening is their signs are going to alternate from plus to minus to plus to minus. So keep that in mind as we proceed. So from now on, when we see a minus, instead of having to go through this step and rewriting like this, we're going to do the expansion like we would normally, except we're going to alternate the signs. All right, so now we're going to apply this to this expression. We want to find quantity square root of x minus square root of y to the power of 6. And to find the 6th power of square root of x minus square root of y, we're going to go to the 6th row. So the coefficients of interest are going to be 1, 6, 15, 20, 15, 6, and 1. And remember that we start with the first term, so we have square root of x minus square root of y all to the power of 6. So we have the first coefficient is 1 times the first term, which is square root of x. So in other words, what normally is x is going to be replaced with square root of x, and what is normally y is going to be replaced with square root of y. So, and then we raise that to the power of n, which is 6. Remember, we alternate signs, right? Because it's a difference rather than a sum. So the first one was positive. The next one will be minus. The coefficient is 6 for the second term. We know that the exponent of this power is going to go down. So we get times quantity square root of x to the power of 5. And now the second radical comes in, times radical y to the power of 1, basically, right? And then the next term will be plus because the signs alternate. So the coefficient is 15. We're going to reduce the exponent of this power one more time. So we get square root of x to the power of 4. And we're going to increase the exponent on this power by 1. So we get square root of y squared plus, or minus rather, remember, positive, negative, positive, negative. All right, so reduce the exponent on square root of x, so it becomes cubed, and increase the one on the square root of y, so that becomes square root of y cubed. And the exponent was that's first, second, third, fourth term, so 20. I need to write a 20. I need to get a 20 in there. So minus 20. All right, so for the next term, we're going to go back to plus 15. There's the coefficient there, times, we're going to reduce the exponent on the square root of x to 2 and increase the one on square root of y to 4. And then we have plus, minus 6 times square root of x times square root of y to the power of 5, finally plus square root of y to the power of 6. And the coefficient is 1, right? And we don't need to write the square root of x to the power of 0 because that's just 1. All right, so now we're just going to simplify. So we get the 6th power of square root of x minus square root of y equals. Now, square root of x to the power of 6, remember that's like saying, we're going to do some scratch work down here. That's like saying square root of x squared cubed, right? So we know square root of x squared is just x, right? So that just becomes x cubed minus. Now we have square root of x to the power of 5. So that's like saying square root of x squared, that takes care of square root of x to the 4, that still leaves and square root of x, right? Now we know square root of x squared is just x, so we get x squared radical x. So minus 6x squared radical x, and then there is a radical y. So it's times radical y, but as you know, we can just go ahead and multiply those out under the radical and just write square root of x y. Of course, as long as not both of those are negative. So we'll add that assumption, okay? All right. Plus 15. Now, square root of x to the 4. So let me get rid of these so we can have room for some more. Square root of x to the 4, that's like square root of x squared and then squared. So we get x squared, right? And the square root of y is just y, right? Minus. Now 20 times square root of x cubed. Remember, that's square root of x squared, which is x times another radical x. Forget the 20. And for square root of y cubed, that's just y radical y. We're probably going to write one more line anyway to really clean it up. Plus 15 x, remember the square root of y to the 4 is like square root of y squared, so it's just y squared, minus 6. Oh, here I put radical 5. Of course, I meant radical y, right? So radical y to the 5, radical y to the 4 is y squared. So we have 6 radical x, y squared radical y. And the square root of y to the 6, just like the first term, becomes just y cubed. All right, so now final cleanup. So x cubed minus 6x squared square root of xy plus 15x squared y minus 20xy radical xy plus 15xy squared minus 6y squared radical xy plus y cubed. And that should be our final simplified version. We try to see if we have any like terms, and be careful, that looks tempting, but they're not really like term, because this is x squared y, but that's xy squared, etc. Same with these two, they kind of look similar, but they're not, because this is 6x squared radical xy, or negative 6x squared radical xy, and this one is negative 6y squared radical xy. So that should pretty much be as simple as it's going to get. So with a clever kind of substitution, we can actually handle expressions with two terms that are not polynomials, but rather non-polynomial expressions as well. All right, so let's go ahead and move on. Make sure you can handle something like that on your own before you proceed. Next, we want to look at a concept called a factorial, which will help us come up with a more efficient way of handling binomial expansions. Now, Pascal's triangle does provide a brilliant method of finding the coefficients of a binomial expansion of quantity x plus y to the n. That said, the process can become quite arduous for large values of n, because you have to sit there and generate a Pascal's triangle for many different rows, right? There's a much more efficient approach to binomial expansions that incorporates a concept known as factorial. If you're only dealing with, say, powers up to 6, 7 even, you can still go with Pascal's triangle. But for anything higher than that, we usually go with another technique, which we'll learn next. First, we need to know what a factorial is. For any natural number n, we denote n factorial, which by this notation, we write an n and then an exclamation mark. When you see this, you don't want to say n exclamation mark. If you're reading a math book, you're going to say n factorial. And we define it as follows. N factorial equals n times n minus 1 times n minus 2, all the way up to down to 1. So in other words, just start with the number and then multiply it by 1 less than it. For example, if you start with 8, the next one would be 8 minus 1, which is 7. The next one would be 8 minus 2, which is 6, etc., all the way till you get to 1. You multiply that out and you have n factorial. Because of the way things are going to work out, we also need to define 0 factorial to be 1. Don't try to look for a rational reason for why that is true. It just happens to be what we need it to be for our computations that we're going to build based on the concept of factorial to work out. So it is the way we're defining it, and we're going to be using it. Next, we want to find these factorials. So 0 factorial, as we just discussed, is 1. 1 factorial is just going to be 1, because, what comes after 1, we stop with the natural number 1 when we do a factorial. So that's where it's going to end. It's just going to be 1. 2 factorial is going to be 2 times 1, which is 2. 3 factorial is going to be 3 times 2 times 1, which is 6. 7 factorial is going to be 7 times 6 times 5 times 4 times 3 times 2 times 1. Now we can of course handle that by just typing it in. 7 times 6 times 5 times 4 times 3 times 2. Of course, we don't need to write the times 1, because we know that's not going to make a difference. So we end up with that. However, as you can imagine, if we have to do this for, say, 12 factorial, that's a lot of writing. So of course, the builders of these calculators have thought about that, and there is a factorial function on here. I'll show you how to get to it. So you're going to click on this toolbox here. You're going to go to probability and then choose factorial. But before you do that, you're going to want to go ahead and type in what factorial you want. So you type in the 7 first, then click on the toolbox, probability, factorial, and then hit enter. You of course get the same answer. Okay, so we do have an option there. All right. But you certainly don't want to be just dependent on a calculator for your understanding of a factorial, because if they give you something like part 6, you should be able to handle it. So, of course, just applying the definition of factorial, this is just some natural number, right? So it's going to be, you're going to start with that number. Notice with 7 factorial, we start with 7. 3 factorial, we start with 3, right? So you start with n minus 3. And what's the next number? That's 1 less than that. So what's n minus 3 minus 1? That's n minus 4, right? So it'll be times n minus 4. And then 1 less again, so that'll be n minus what? 5. What's n minus 4 minus 1? That's n minus 5, right? Now you don't have to write a million of these. Just go at this point dot dot dot, and then you're going to go all the way to 3 times 2 times 1. All right, and that's how you would want to show what quantity n minus 3 factorial is. All right, let's go ahead and take a look at this expression. So we have 6 factorial over 2 factorial times 4 factorial. Now, rather than just typing this into a calculator, you should work it out by hand, because that gives you a lot of insight into factorial. So we have 6 times 5 times 4 times 3 times 2 times 1. Now down below we have 2 factorial, that's 2 times 1, and 4 factorial, that's 4 times 3 times 2 times 1. Notice you can do a lot of cancellation here. All of those will cancel all of those, right? So basically all you have is 6 times 5 divided by 2, right? Notice that I can cross cancel the 2 and the 6 to leave me 3. So all I need to worry about now is 3 times 5, which is 15. Okay? We can of course verify using a calculator. So we have 6 toolbox probability factorial divided by, not like that, actually let me use parentheses, 6 toolbox probability factorial, and then we'll get out of the parentheses, go divided by quantity 2 toolbox probability factorial, and then times 4 toolbox probability factorial. And of course we end up with the same thing. But you should definitely be able to handle something like this without a calculator. As we move toward coming up with an alternative way of handling binomial expansions, we need to next understand what the binomial coefficient is, so that we have a method other than Pascal's triangle at our disposal. Okay, to that end, we're going to consider a simple expansion like the 4th power of x plus y. Now we've seen that the 4th power of x plus y is x to the 4 plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the 4. Now the first and last term are pretty simple. We know what they are, right? So let's look at the second term, 3rd and 4th, okay? Notice that the second term of the expansion is 4x cubed y to the 1, right? Now I'm going to write the ones for emphasis because we need to think about them in a minute. Notice that the coefficient of the second term is 4, and the exponents are x and y, of x and y are 3. Notice the coefficient on x, and 1 for y. Also notice that if I take 4 factorial, which is basically n factorial, and divide it by the first exponent factorial times the second exponent factorial, that means 3 factorial times 1 factorial. Notice what happens. I get 4 times 3 times 2 times 1 divided by 3 times 2 times 1, which is 3 factorial, times 1 factorial, which is 1. So these will cancel these, and we just end up with 4, which happens to be that same coefficient that we started with, right? Now, look at the third term of the expansion, 6x squared y squared. Notice that the coefficient is 6, and the exponents of x and y are 2 and 2. So if I look at, again, on the top, I'm going to have n factorial, which is 4 factorial, and I divide that by the factorials of these two numbers. In other words, 2 factorial times 2 factorial, we end up with 4 times 3 times 2 times 1 divided by 2 times 1 times 2 times 1, right? So you can see cancellations here. 2 and 4 leave us 2 on top. 2 times 3 is 6. Again, you see it's the same coefficient. So this expression would give us the coefficient even if we didn't have it, right? Notice that the coefficient of the fourth term, again, is 4. And the exponents of x and y are 1 and 3. So if we do 4 factorial, notice the top doesn't change. It's always n factorial. Divided by the first coefficient exponent factorial times the second exponent factorial, we end up with 4 times 3 times 2 times 1 over 1 factorial, which is 1, times 3 factorial, which is 3 times 2 times 1. These cancel these, we get 4 again, which is the coefficient. Now we're going to generalize this notion. All right, if we generalize this notion to the coefficient of the term in the expansion of the nth power of x plus y, for which the variable part is x to the r, y to the n minus r, we obtain the following value for the coefficient. First of all, convince yourself that this is a proper term of such an expansion. Remember, for these kinds of expansions, right, for each term, the coefficient on x and the coefficient on y should add up to the n that you start with, which is the exponent you're raising the original binomial to the power of. And here, notice what is r plus n minus r. Notice that the two r's will cancel out and you end up with what? With n. So it's consistent. So of course we're going to get n factorial, remember, divided by the first exponent factorial, so that's where r factorial comes from, times the second exponent, the exponent of the y, which is n minus r factorial. This number here is called the binomial coefficient and usually denoted using either this notation, kind of like a matrix notation, right? Or just like this, NCR. Now, both of these should be read N choose R. Now, some of you who've had probability before may recognize this particular expression. And I want you to know that it's the same NCR that you had seen in probability when studying combinations and permutations, in particular combinations. In the context of binomial expansions, we usually use this notation rather than this notation. But, you know, it's not set in stone. You may see this notation as well. Note that these binomial coefficients are the same numbers that you would find in Pascal's triangle. For example, this particular matrix here for 4 choose 0 would be add 1 to the bottom row, so the bottom element, so 0 plus 1 is what? 1. So this would be the first number in, and this is going to be the row number in the fourth row of the Pascal's triangle, right? And 6, 3, for example, would be the fourth. Remember, add 1 to this number down here. So that tells you what number in, and this top one is always the row number. So this would be the fourth number in row 6. If we take a quick look at Pascal's triangle, we would know what 6, 3 is real quickly without even doing this. But of course, we need to know how to do that. But this is kind of handy as well. So 6, 3 would be the fourth number in row 6. So here's row 6. So we want the, my memory is failing me, fourth number, right? Yes, I was right. Fourth number in row 6. So here's row 6, 1, 2, 3, 4. So this should end up being 20, right? So we'll find out whether it is or not, of course, by computation as well. All right, so if we look at 6(3), we know that it should be 6 factorial divided by, remember, r here is 3, so 3 factorial times n minus r, so 6 minus 3 factorial. So it would be 6 factorial divided by 3 factorial times 3 factorial. So we would have 6 times 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1 times 3 times 2 times 1. Of course, a lot of things cancel out. Those 3 cancel those 3. These 2, 3 and 2 cancel the 6, right? So we have 5 times 4, which is what? Which is 20, as we just discovered using Pascal's triangle. All right, here's another one. Go ahead and figure that out without using a calculator before you continue to watch. Okay, so of course, I reminded you of the formula you need to use. So we have 9, 5. We know that should be 9 factorial divided by 5 factorial times quantity 9 minus 5 factorial, right? So we get 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 5 times 4 times 3 times 2 times 1 times 4 factorial, which is 4 times 3 times 2 times 1. Now we can see cancellations. Those cancel those, right? 3 and 2 cancel the 6, right? 4 and 8 leave you 2. So all we have left is 9 times 2 times 7, right? So basically we have 18 times 7, right? Which is like saying 10 plus 8 times 7, since we said no calculator. So that'll be 70 plus 56, which is 126, like so, okay? Now, sometimes when you see something like 9 factorial divided by 5 factorial, one clever way of handling that is to realize that that's like, remember, this is a different problem I'm showing you now. We're finished with the problem we were doing, okay? Just want to show you how to handle a simple thing like that. You can just go, that's 9 times 8 times 7 times 6 times what? Times 5 times 4 times 3 times 2 times 1, which is just what? Which is 5 factorial, right? And then divided by 5 factorial, and then cancel those, and you just get 9 times 8 times 7 times 6. So that's kind of a nice way of handling a problem like that too. That, of course, you can either do by hand or plug into a calculator, okay? So there you have that. Okay, so here we have 9C2. We're going to use the trick we just learned about. So see if you can figure out what I mean by using the trick I just showed you, and then come back. So remember, this is 9C2, which is, of course, just another notation, you know, for this 9 choose 2. That's how you should really say it, 9 choose 2. All right, so 9 choose 2 is going to be 9 factorial over 2 factorial times 9 minus 2, which is 7 factorial. Now remember, that means I can say 9 times 8 times what comes after 8, 7 times 6 times 5, etc., which is just 7 factorial, right? Divided by 2 factorial times 7 factorial. So notice how nice and simple that is. You can now cancel out the 7 factorials. And 2 factorial is, of course, just 2, right? So basically, we have just 9 times 8 over 2. 2 and 8 cross-cancel to leave us 4. So we get 9 times 4, which is 36. So that is 9, choose 2. All right. It's a nice use of our little trick there. All right, here's one that you should be able to do without basically any work if you really understand what that refers to in the Pascal's triangle, right? Remember, you have to add 1 to that. So that means this is the 11th number in the 10th row of Pascal's triangle, right? So that's the expansion of x plus y to the power of 10. So basically it's the last number. What's the last number going to be? That's going to be y to the 10, right? So what is the coefficient? This is going to be the coefficient, of course, of that term, right? So you know that should be what? 1, right? But now let's verify it. We know it's going to be 10 factorial divided by, we're computing 10, 10, right? So it's 10 factorial divided by 10 factorial times 10 minus 10 factorial, right? So basically it's 10 factorial divided by 10 factorial times 0 factorial. Remember what 0 factorial is? That's 1. So it's 10 factorial divided by 10 factorial, which is what? 1. Just as we expected it to be, right? So understanding the connection between these and Pascal's triangle can help you be more efficient. Here's another one you should be able to answer immediately, right? Because we know that 15 choose 0 is the same as this notation, the matrix with 15 and 0 in it, which is basically, remember, add 1 to 0. So that means it's the first number or the first coefficient in the 15th row of Pascal's triangle, right? So it's the first coefficient in the expansion of quantity x plus y to the power of 15. So we know that what that's going to be. That's going to be x to the 15, right? So what's the coefficient? 1. Now let's verify it. So according to our formula here, it's going to be 15 factorial divided by 0 factorial, right? Times 15 minus 0 factorial. So it's going to be 15 factorial over, we know 0 factorial is 1. So it's just going to be over 15 factorial, which is 1, as expected, right? So what we've just done, the past couple of examples, should have made you realize that we have a symmetry very similar to what we've observed in Pascal's triangle, which is basically n choose r is the same as n choose n minus r. Why is that? Because we know what nr is, right? N choose r is n factorial over r factorial times quantity n minus r factorial. And what is n choose n minus r? Well, that's going to be n factorial over quantity n minus r factorial times, remember what this is going to be. This is going to be n minus whatever this is, right? So what is n minus quantity n minus r? Well, it's going to be n minus n plus r, which is what? Which is r. That's why we have r factorial here, okay? So it's a trick you may sometimes be able to use in a handy way. We're finally ready to state the binomial theorem. All right, so for any natural number n and xy belonging to the set of complex numbers, we have quantity x plus y to the n is going to be, okay, so remember, to get the coefficient of the first term, we use n0, and we know what the exponent is going to be on x, that's going to be n. Now, for the powers of x, just keep going down by 1. So the next one is n minus 1, n minus 2, n minus 3, all the way up to where it becomes 1 and then 0 here. This is going to be x to the 0, which we don't write. For the powers of y, start with y to the 0 here, which is going to be 1, which we don't write. The next will be 1, 2, 3, all the way up to n. And the coefficients start with n0, then go to with n1, n2, n3, all the way up to nn. And of course, we know, just as was the case in Pascal's triangle, the coefficient of the first term and the last term are these two, which we know and we've already seen examples of. They're both going to turn out to be 1. Now, this expression right here, right, is quite daunting, right? But if you remember the summation notation, if I use r for the summation index, I can just rewrite this sum as the sum from r equals 0 to n of n choose r times x to the n minus r, y to the r. So think about that for a second, see if it makes sense. Plug in 0, right? Start with 0. So what's n0? Right there. And what is n choose 0, right? And what is x to the n minus r going to be? Remember, r is 0, n minus 0 is just n. So we get x to the n. And y to the 0, that's 1. So that's why we don't need to write it, because x to the n times y is just x to the n. What's now run through value of 1 for r, right? Remember, we just run through the values of r and we add. So it's going to be plus, now n, let r be 1, so we get n choose 1. For the exponent, we're going, for the term, we're going to get x to the power of n minus 1. That's where this comes from. And then y to the power of r, which is 1. So that's just y, right? What's the next one going to be? n2, right here. X to the n minus 2, and then y to the what? R, which is 2, etc. So you can see this entire sum can be compactified into this nice summation format here, right? Which is a lot easier to remember. Okay, let's go ahead and apply the binomial theorem. So let's go ahead and find the binomial expansion of quantity a plus b to the 9. So we know that this is the formula we're going to use. So it's going to be the sum from r equals 0, in this case n is 9, so to 9, of 9 choose r times x to the 9 minus r, y to the r, like that. So go ahead and see if you can write that expansion out on your own completely. Write all the 9 terms in the sum, okay? It's a summation. All right, so starting with r equals 0, right? So we get 9 choose 0, x to the 9 minus 0, y to the 0, right? Plus, the next one will be 9 choose 1, x to the 9 minus 1, y to the 1. The next one will be, so plus 9 choose 2, x to the 9 minus 2. We're running the value of r equals 2, right? And then y to the r, which is 2, plus 9 choose 3, x to the 9 minus 3, and then y cubed, plus 9 choose 4, x to the 9 minus 4, y to the 4, plus 9 choose 5, x to the 9 minus 5, y to the 5, plus 9 choose 6, x to the 9 minus 6, y to the 6, plus 9 choose 7, x to the 9 minus 7, y to the 7, plus, we're getting there, 9 choose 8, x to the 9 minus 8, y to the 8, and finally 9 choose 9, x to the 9 minus 9, y to the 9. All right. So we have 9 factorial over 0 factorial times 9 minus 0 factorial, which is 9 factorial, x to the 9, y to the 0 here is just 1, so we won't write it because 1 times any expression is the expression, plus 9 1, so 9 factorial over 1 factorial times 9 minus 1, which is 8 factorial, x to the 8, y to the 1, which is just y, plus 9 factorial over 2 factorial, right, times 9 minus 2, which is 7 factorial, then x to the 7, y squared, plus 9 factorial over 3 factorial times 6 factorial, x to the 6, y cubed, plus 9 factorial over 4 factorial times 9 minus 4, which is 5 factorial, x to the 5, y to the 4, plus 9 factorial over 5 factorial times 4 factorial, which is 9 minus 5, times x to the 4, y to the 5, plus 9 factorial over 6 factorial times 9 minus 6, which is 3 factorial, x cubed, y to the 6, plus 9 factorial over 7 factorial times 9 minus 7, which is 2 factorial, x to the 2nd power, and then y to the 7, plus 9 factorial over 8 factorial times 9 minus 1, which is 1 factorial, x to the 1, y to the 8, plus 9 factorial over 9 factorial times 0 factorial. X to the 0 is 1, we won't write it. Y to the 9. There it is. So all we have to do is just compute those and we're done. So for this, since we've done so much work with these, we're going to be efficient and do them quickly. So we know that this is just going to be 1, right? So we get x to the 9 plus 9 factorial over 8 factorial. Remember, that's just like saying 9 times 8 factorial over 8 factorial. So the 8 factorials will cancel out, so we just get what? 9 times x to the 8 y plus 9 times 8 times 7 factorial over 2 factorial times 7 factorial. The 7 factorials cancel out, so we get 2 factorial is just 2. So we get 36, right? So we just figured out this here is just 9. This is 36, right? And then x to the 7 y squared plus 9 times 8 times 7 times 6 factorial divided by 3 times 2 times 1 times 6 factorial, right? So the 6 factorials will cancel out, and 3 goes into 9 3 times, 2 goes into 8 4 times. So basically we have 12 times 7, which is 84. So this coefficient here is 84. And we have x to the 6 y cubed plus. All right, so we've got the gist of this. Let's go ahead and use a calculator now. Actually, this is where we're going so far. There's only one more unique one we need to figure out, right? This one, the 4 factor, this one. Because the rest of them, remember, there's symmetry. They're just going to be the same. Remember, 9 factorial over 6 factorial times 3 factorial is the same as 9 factorial over 3 factorial times 6 factorial, etc. So all we need to do is one more. So let's just go ahead and do it. So we have 9 times 8 times 7 times 6 times 5 factorial divided by 4 times 3 times 2 times 1 times 5 factorial. The 5 factorials will cancel out. 4 and 8 leave us 2, and 2 and 6 leave us 3, and 3 and 3 cancel out. So we have 63 times 2, which is 126. So this guy here is 126. And then it's times x to the 5 y to the 4 plus. Now we just figured out what this is, because 4 factorial times 5 factorial is the same as 5 factorial times 4 factorial. So that's going to be 126 again. So we won't repeat what we just did. So that's just going to be 1 to the 6 x to the 4 y to the 5 plus we are here, which we've already computed. What is this one? 84. And it's going to be x cubed y to the 6 and then plus, we've computed this one before right here, so that's 36 x squared y to the 7 plus, we've computed this one before over here, that's 9, and finally we know what that last one is, right? That's just 9 factorial. Well, 9 factorial, which is 1, so y to the 9. That's it. So we just clean it up and we're done. So we get equals x to the 9 plus 9x to the 8y plus 36x to the 7y squared plus 84x to the 6y cubed plus 126 x to the 5 y to the 4 plus 126 x to the 4 y to the 5 plus 84 x cubed y to the 6 plus 36 x squared y to the 7 plus 9x y to the 8 plus y to the 9. All right, so definitely in the category of what we call tedious but not difficult, right? Lots of details. You got to make sure you don't make any errors, but it's really not very difficult, is it? As painful as it may seem, you do need to be able to run through something like this on your own so that you have mastered the concept. Okay, so that's that. Okay, I just noticed there's one thing more that we need to do for this problem. Notice we did the expansion with x and y, right? But the rest is pretty much trivial because all we're going to do is replace all x's with a's and all y's with b. So as a final step, we're going to say quantity a plus b to the 9 is equal to a to the 9 plus 9a to the 8b plus 36 a to the 7 b squared plus 84 a to the 6 b cubed plus 126 a to the 4 a to the 5, sorry, b to the 4 plus another 126 a to the 4 b to the 5 plus 84 a cubed b to the 6 plus 36 a squared b to the 7 plus 9 a b to the 8 plus b to the 9. This can actually be applied to all kinds of complex expressions. I've done it before where I just use the modified letters right away. And in this one, we ran through it with just going with x and y and doing a substitution at the very end. They both work. Do notice that all the observations we had work. All the coefficients in the terms, the exponents of the variables add up to the n, which is 9, etc. So pay attention to the fact that all of our general observations are valid here as well. Okay, so this time we're really done with this problem and we can move on. All right, here's one more expansion. This time the expression that's being raised to a power is a little bit more complex, but at least we're only going to the power of 5, right? So what I want to do this time is run it straight through, right? Run it directly without having to do a substitution at the end. So this is the general summation form of what we need to carry out. However, we're going to modify it, right? So we're going to go from r equals 0 to n, which is 5. Instead of nr, we'll have 5 choose r. For x to the n minus r, the x is the same, it remains x, so we get x to the 5 minus r. But instead of y to the r, we're going to use this expression because we can think of this as a sum, right? So think of it as x plus quantity negative 1/2 y, and then raise the whole thing to the power of 5, like that. So negative 1/2 y. So that's why we're using negative 1/2 y in this second slot here, okay? And that's going to be raised to the power of r. Now we're going to run through the summation, right? See if you can do it yourself first and then come back. So we're starting with r equals 0, right? So we get 5 choose 0 times x to the power of 5 minus 0 times quantity negative 1/2 y to the power of 0 plus 5 choose 1. Now we're at r equals 2, right? 1. So 5 choose 1 times x to the 5 minus 1, which is 4, times quantity negative 1/2 y to the power of 1 plus 5 choose 2 x to the 5 minus 2, which is 3, times quantity negative 1/2 y to the power of 5 minus 3, which is 2, and then 5 choose 3 x to the 5 minus 3, which is 2, times quantity negative 1/2 y to the power of 3, which is r, right? And then plus 5 choose 4 x to the power of 5 minus 4, which is 1, which we don't need to write, times quantity negative 1/2 y to the power of 4 plus 5 choose 5 x to the 0 times quantity negative 1/2 y to the power of 5. Now it pays to go through and make sure that we haven't made any quick errors. So 5 0, 5 minus 0 times negative 1/2 y to the 0 plus 5 1 x to the 5 minus 1, which is 4, negative 1/2 y to the 1, which is correct, plus 5 2 x to the 5 minus 2, which is 3, times negative 1/2 y to the power of 2 plus 5, 3 times x to the 5 minus 3, which is 2 times quantity negative 1/2 y to the power of 3, which is r, 5, 4, x to the power of 5 minus 4 times negative 1/2 y to the power of 4, which is r, plus 5, 5, x to the 5 minus 5, which is 0, times negative 1/2 y to the power of 5, which is r. Okay, so now we just simplify and we'll be good to go. Now, we've done enough of these to know. So basically we have x minus 1/2 y, and then we're going to raise the whole thing to the power of 5 is going to be equal to, all right, we've done enough to know 5, 0 is just going to be 1, so x to the 5, and we know that this is 1, so we don't need to write it, times 1 is just itself, so plus 5, 1, which is 5 factorial over, now I could write 1 factorial, but I know that 5, 1 is the same as 5, 4. Remember? Let me show you why. Remember this fact? NR is the same as N minus R. Now, let's see why this is helpful. So remember, this is the fact we're going to use. So down here, I'm going to show you, I can do 5, 1 would require me to do 5 factorial over 1 factorial times 4 factorial, right? But if I use 5, 4, I would end up with 5 factorial over 4 factorial times 1 factorial. So I basically end up with the same thing, right? So why would I want to have this first? Just because it might help me quickly remember that I can then just do this. 5 times 4 factorial over 4 factorial, this is just 1, and these canceling out and giving me what? 5. So that would be the only reason, because I would be more likely to remember to use this trick. Otherwise, they're pretty much the same thing. Okay, so, and also I wanted to remind you about this little nifty rule that you can apply. Okay, so let's go ahead and move on. So over 4 factorial times 1 factorial, and then it'll be x to the 4 times negative 1/2 y plus 5 factorial over 2 factorial times 5 minus 2, which is 3 factorial, and then x cubed, and this will give me 1/4 y squared, right? Positive. Plus, now we're here, 5, 3, so 5 factorial over 3 factorial times 2 factorial x squared times, this will be negative 1/8 y cubed plus, we're handling this term now, so 5 factorial over 4 factorial times 1 factorial times x times, this will give us positive 1/16 y to the 4, and then plus, we know 5, 5 is 1, x to the 0 is 1, so we're just going to get negative 1/32 y to the 5th. All right, a little bit more simplification and we'll be done. Let's, we already did 5 factorial over 4 factorial times 1 factorial. Remember, that's just 5. Now, I'm going to do some scratch work down here. 5 factorial divided by 2 times 1. I'm handling this one right here. Times 3 times 2 times 1. So that's 5 times 4 times 3 factorial over 2 times 1 times, I could have just left that as 3 factorial. These cancel out. 20 over 2, 10. So this guy here is 10. Here we have the same basic expression. We're simplifying. We know that's going to be 10. We've already figured this one out. That's 5. And that's it as far as those factorials. Let me go ahead and get rid of these. All right, so we're almost there. So the 5th power of x minus 1/2 y is going to be x to the 5. Now here I have positive 5 times negative 1/2, so that's going to be minus 5/2 x to the 4 y. And then we have positive 10 times positive 1/4. That's 10 over 4, which is the same as 5 over 2. So plus 5/2 x cubed y squared. Next we have 10 times negative 1/8, right? So that's negative 10 over 8 or negative 5/4. And then we have x squared y cubed. For the next one, we have positive 5 times positive 1/16. So that's going to be plus 5/16 x y to the 4th. And finally, that's just going to be positive times negative is negative 1 over 32 y to the 5th. There it is. We have the expansion right there, and we are done with that. Make sure you satisfy yourself that all our basic observations work, and we do have 1, 2, 3, 4, 5, 6 terms, etc. So satisfy yourself that this is the correct answer. All right, and also make sure you can do it on your own. Nothing difficult. Again, tedious but not difficult. Do also notice that the signs alternate because it was a difference that we were finding the expansion of, the binomial expansion of positive, negative, positive, negative, positive, negative. All right, that's that for this problem. Just one more quick topic and we are done. Not only with this lesson, but with this class, okay? All right, so the last thing we're going to do is find the kth term of a binomial expansion without actually doing the expansion. Suppose we want to find the 12th term of the expansion of the quantity x plus y to the n. Of course, here we would want n to be greater than or equal to 12 since we want the 12th term without having to find the whole expansion. So we firstly need to note that in the 12th term, y would be raised to the what power? Think about it, in the 12th term, right? Well, if you're doing x plus y to the n, what's the exponent of y going to be in the first term? The first term is just going to be x to the n, right? So the exponent of y is going to be 0, right? And what's the exponent of y going to be in the second term? Well, it's going to be 1, etc. So always 1 less than the term number, right? So for the 12th term, the exponent on the y would be what? Would be 11, right? Now, given that the exponents of the powers of x and y must add up to n, as you know, in each term, so we want to know 11 plus what number gives us n? Just solve this for the question mark and you end up with n minus 11. So now we can write the 12th term of the expansion. We know the coefficient is going to be n11, right, times x to the power of n minus 11 times y to the power of 11, which is going to be n factorial over 11 factorial times n minus 11 factorial, x to the n minus 11, y to the 11. Now, if we generalize the kth term of the binomial expansion of x plus y to the n for n greater than or equal to k minus 1 is going to be given by n. Remember, for the 12th term, we had 11, so that's 12 minus 1. So for the kth term, we're going to have what? K minus 1. And then x to the power of n minus whatever that k minus 1 is, times y to the power of k minus 1. That's how you would find the kth term without actually having to find the whole expansion. All right, so here's our last example of the lecture and the course. So we're going to find the middle term of the expansion of quantity 6x to the 4 plus 2y squared to the power of 10. We know that the kth term can be obtained with this formula, which we just developed. The only thing is we need to be careful because obviously we're going to use a different expression for x and a different one for y. So where we see x here, we're going to replace it with 6x to the 4, and where we see y, we're going to replace it with 2y squared. Now we can see that n is 10, and we need to find k, because they don't tell us which term, which they say the middle term. Now remember, you have a 10th power expansion, so that means we're going to have 11 terms. So that means the middle term is going to be what? Well, if we take 11 divided by 2, that gives us 5.5. So just round that up to 6 to see what the middle term is. So the middle term is the 6th term. So basically, instead of this, we could have been nicer and told you to find the 6th term. But there, just for extra practice, right? So we want the 6th term. So k equals 6. That means k minus 1, which we also need to work with, is going to be 5. So we end up with 10, choose k minus 1, which remember is 5, times, remember, instead of x, we're going to use 6x to the 4. And the exponent on that is going to be 10 minus k minus 1, which is 5. So 10 minus 5, so 5, right? And instead of y, we're going to use 2y squared. And the exponent on that is just k minus 1, which is 5. Like so, okay? So basically, we're looking at 10 factorial divided by 5 factorial times 10 minus 5 factorial, which is another 5 factorial, times 6 to the 5 times 2 to the 5, and then x to the power of using the power rule gives us 20, y to the power of 2 times 5, which is 10. Now, 6 to the 5 times 2 to the 5, since the exponents are the same, we can just write it as 12 to the 5. So 10 factorial over 5 factorial times 5 factorial, and then this is going to be times 12 to the 5 on the top. X to the 20, y to the 10. All right, and now that we're all tired, we're going to go ahead and just plug that into a calculator. All right, so we're going to have quantity 10 factorial. Remember, click this toolbox and then probability and then factorial. And then times 12 to the power of 5. We're going to exit the parentheses now and then hit divided by 5 toolbox probability factorial times 5 toolbox probability factorial. And then we just hit enter. So there we have it. So 62,705,664. Let's make sure I wrote that correctly. 62 million. Oh, 705 and then 664. So that should be a 5. See why it's good to always double check? Because if you make an error, as long as you're careful and you double check or even triple check, you'll catch it. All right, and then x to the 20, y to the 10. And there is the 6th term of the expansion of this binomial power without having to find the entire expansion. Okay, that's it. That brings us to the end of the road. I hope you have enjoyed the class, and I wish you success in all your future endeavors. Hopefully, we can meet again for some other class. Take care and see you later.